Ivan Baev, and I'll be talking today about controlling virtual register pressure in middle-end optimizations. Here's the outline. I'll start with motivation for our work, followed by brief overview of related work, followed by several definitions of register pressure. Then I'll proceed with analysis of loop invariant code motion paths in respect to register pressure, followed by our algorithm for control it. Then we'll do a similar process for the GVN path, followed by performance results on ARM processor. Then I briefly describe the future work on enhancing inliner with register pressure heuristics, and conclude with summary. When you compare LTO plus OFAST against just OFAST performance, unfortunately, we saw about 10% degradation in crafty benchmark. Our analysis revealed that the three passes are mostly responsible for this impact. Inliner, loop invariant code motion, and GVN, roughly 3% each of them. Also, we observe extra spill code at the final assembly, and using perf2, we saw additional execution time in two of the top routines evaluated in swap. And this led us to conclude that the root cause is obviously increased register pressure. And I'd like to say that this scenario is typical for other compilers too, especially when one is trying to introduce or enable new optimization, especially loop-based ones, or increasing the optimization level. For most outliers, one common reason for degradation is increased register pressure. So this problem of register pressure has been known for compilers, engineers, and performance people for many years. And the root cause is the actually mismatch between the infinite number of registers assumed by most compiler optimizations and the finite numbers that the hardware processor provides. Over the years, there's been a lot of work to address this problem, mostly at machine level IA, especially in register locator and scheduler and passes around those. One early attempt is rematerialization, where we try to split life ranges by recomputing instead of spilling. Then second paper listed several techniques to handle register pressure in GCC at the beginning of century, one of which was splitting life ranges on loop boundaries. The other one is life range shrinking implemented within the register pressure sensitive scheduler. Then another optimization for reducing register pressure is prematerialization, which is good for processor with NOP instructions, where we recompute and place the new definition in the NOP slot, basically achieving register pressure for free. Another one is to use region-based register locator as a way to achieve substantial life range splitting across region boundaries. And then, of course, there are several works on implementing register pressure scheduling. And within LLVM, there is a very good infrastructure for tracking register pressure, and it used for register pressure aware scheduler, presented at the same forum 2 years ago by Andy Trick. Also, there is some work at high-level IA, most notably in LICM, partial redundancy elimination, and loop transformation. So in general, for all redundancy elimination transformation, the goal is to reduce the number of instructions. But that valid objective usually creates fewer but more complex life ranges and naturally increase register pressure. So the three papers cited try to accomplish optimization goals being aware of register pressure. Inlining is a very interesting path in this in previous research, although most paper acknowledge the importance of register pressure due to inlining. They do not address this issue, so they do not use register pressure in ranking function, for example, or goodness factor when compare hot side, which is probably assume the problem is difficult to solve. So the conclusion from the previous research seems to indicate that handling register pressure at a single place, for example, in register locator or scheduler, is usually not sufficient. In this talk, we'll focus on mainly on middle-end target-independent optimizations. So before giving details about our approach, let's define more carefully virtual register pressure. So at a given program point, a register pressure is equal to the number of overlapping life ranges at this point. And we can extend this definition at basic block, loop, or function by picking or computing the highest register pressure over all program points in the entity. And one simplification of this definition is what we do actually in this work for basic block or loop. So we define register pressure to be the number of live fins for the basic block or loop. And we definitely need to distinguish between integer register pressure that deals with computation and liveness of integer or general purpose registers versus floating point or predicate register pressure if the processor supports a predicate register class. And one important thing to note here is that register pressure computation is always approximation. And there are many reasons that lead to this approximation. There's potential promotion of memory into registers. Effective cause is very often unknown. And there is a register pair in many processors where we can put together two values in a single register, and many others. And final note is there is trade-off between precision and compile time. Effectively, for better, more precise register pressure estimate, we need more complicated analysis, especially data flow analysis. I'll start with describing some basic idea of our approach, especially in the framework of LLVM. We take a pass and analyze it, especially its main components with respect to register pressure, basically by studying the code and collecting various statistics. Then once we pick the components with the highest register pressure impact, we add a measure of register pressure and control those components, basically control their aggressiveness of performing their optimization. So since the LLVM passes can be invoked multiple times, need to make sure that our controlling logic can also be invoked multiple times. And we always include a comparison with the number of hardware registers for a given class for the target processor. So let me start with register pressure analysis of LLVM loop invariant code motion passed. as many of you already know, it is loop level pass with three major components: syncing code, hoisting code, and promotion and memory location. So let's consider first syncing code, the first part, and by its action by syncing code basically moves computation in the exit basic blocks of the loop, and because of that, it's not likely to impact register pressure in terms of the number of live fins for the loop. Now, the second component, hoisting, do impact register pressure, and on the screen I am showing 4 instances of the instruction to be hoisted and their impact on register pressure. So the first is load from a global, second is load from a field of a global, and both instructions increase register pressure or number of live fins by 1 by adding the destination register to the number of live fins for the loop. The third example I compare, one source operand is constant, but the second one, we assume that it's only used in this instruction, so the overall effect on register pressure by hoisting this instruction is 0. And then there are certain instances where we decrease register pressure by 1, if you assume that both sources are used only in this instruction. So we definitely need to model register pressure for this hoisting component. And the third component is promotion of memory locations. And the conclusion is that it's not likely to substantially increase register pressure. And here's one common example when we increment the value at particular loop invariant memory location. So on the left side, the value that is holding the address A is part of the live in. And on the right side of the slide, we perform the promotion of memory location. So in this case, we insert load in the preheader and store at the exit block and appropriate fee in the loop. And indeed, we're able to remove A from the live in set, but you need to add Y, variable Y, to the live in. So the net effect is 0. So here's our implementation of register pressure heuristic. The routine estimate register pressure on the loop is invoked at the very beginning of processing of our loop. We iterate over all basic block in the loop, also iterating over the instruction in the basic block and the source operands in the basic block. And if operand is of appropriate type, and it is defined outside the loop, or it is function argument or global variable, we add it to the loop of, we add it to the live in sets. After this processing, we compare the cardinality of live in sets with the maximum hardware registers that are supported by this processor, and we use the get number of registers with false argument, which gives back the integer number of registers. And if the current live ins is greater or equal to that to the maximum number of hardware registers available, we disable further hosting for this loop by setting the max LIS variable to 0. Otherwise, we compute the difference and allow that much hoisting action. So when we actually ready to hoist instruction, that means that all legality conditions are met, so it's legal to hoist this instruction. We just check whether the instruction to be hoisted actually will reduce register pressure, and if that's not the case, and we're exceeding in the current live in ranges exceeded the maximum allowed, we just skip a hoisting action for this instruction. Otherwise, we hoist instruction and properly increment the loop life ins. And the routine at the top does reduce pressure. It just try to compute the number of life ranges that are reduced or increased by hoisting this instruction, and know that the initial value is -1 because you need to account for the destination operand. By hoisting the instruction, we always add destination operand to the life ins. So I continue with the similar approach for LLVM global value numbering pass, but in a shorter time. It is function level pass with two major components. One is the proper GVN, and second one is a simple form of partial redundancy elimination, which operates on a simple diamond shape control flow. And GVN operates mainly on basic block basis and promotes move operation within the basic block. And one exemption of this is process non-local load. And this is a good place. This is the place that can actually increase substantially register pressure for the most benchmarks. So since GVN does not have support for loop structure by default, there's no explicit loop structure, we try first to use basic block register pressure estimate, just by using similar to previous version shown for LICM. But our experiment shows that when we use the register pressure for the loop that encloses the load, not just the block, we achieve much better results. So at the end, we compare the register pressure for the loop to the number of hardware registers. And if the condition is greater or equal, we skip processing and promoting this load. So the next slide shows our evaluation of the both heuristic individually and combined. The first column shows the spec 2000 benchmarks that are impacted from these algorithms. For the remaining 8 C++ spec benchmarks, they do not exhibit performance impact above the noise range, so they're not shown. So the second column shows the speed up with LICM register pressure over LTO, link time optimization. The third column shows performance with GVN algorithm, and the last column shows combined effect of the two heuristics. And the data were obtained with Qualcomm LLVM compiler on Nexus 4 Android devices, which are ARM-v7 type devices in term mode. Couple of observations of this study. So if you look at the last two WOOF that achieve approximately 3% improvement in all three combination, and VPR about 2% on all three combination, that probably indicate that either of the heuristic was able to address register pressure, so we don't see a cumulative effect. However, if you look at the numbers for Crafty and Equate, we did see some good accumulative effect on both heuristic. So for Crafty, the final improvement was 4.3% over LTO, and for Equate, about 1.9. So we also achieve good improvements result in R mode for V7 and also on hexagon processors for OFAST and LTO. And it was very satisfying to to achieve that for both out of order and in order processor. So I'll complete the talk on briefly describing our approach, our future approach of controlling register pressure in inliner. First step is to compute max register pressure for each function traversing call graph in bottom-up order. And when we see a call site, we would add the callee register pressure to the current register pressure of the caller. So the next step, once you got all max register pressure for all functions and all call sites, is to add this value of register pressure to the goodness factor or ranking or cost function to the call site. And since increased register pressure should discourage inlining, and vice versa, small register pressure should encourage inlining decision, this value should be placed as a cost in the denominator. And one observation is that when the total value of register pressure exceeds the available hardware registers, you should add additional costs. Previous research in inliner shows that it's important to update cost functions with each inlining decisions made so that our ranking is kept up to date. But likely, for the first implementation, we don't need to update max register pressure for a function after each of its call site has been in line. So I'm concluding with summary. Most likely, the register pressure would likely to stay. Each new generation of processor support feature more registers. However, we as compiler engineers quickly take advantage of them. And just in no time make extra resources insufficient again. In this talk, we presented a general approach and a specific heuristic for controlling register pressure in 3 components of LLVM middle end. Although not mentioned here, unroller is possibly another good candidate to enhance with similar heuristics. And if there is interest, we'll be happy to upstream those patches. We would like to suggest that new compiler optimization be designed with register pressure in mind. And you would like to point out that in many cases, simple heuristics like that shown in this talk works well. And although this topic was on middle end optimization, as a community, we need to keep improving backend passes for better register pressure handling and generating less spill code. So one nice feature we would like to have that would really help us to in tuning register pressure analysis is if profile information is available to compute the sum of weighted spills for a function, so that at the end of the compilation, you're able to see the total amount of spill code, but in terms of the using profile informations. So because without profile information, this information might be misleading because you may have more spill code in code section, and that is perfectly fine. I'd like to acknowledge contribution of several members of Qualcomm LLVM group, in particular Zhou Zheng, Balram Makam, Yin Ma, and Taylor Simpson. And with that, I'm open for any questions. Thank you.
So in the case of a hoist, an LIC out of a loop, if you're going to reduce the critical path, if you could, if that resulted in a spill that was outside the loop, you might be better off overall. But presumably, it's the case where a spill happens inside the loop, where this optimization or preventing the hoist helps. Is that accurate?
I think I don't disagree with this statement. Yes, but it's just heuristic. I mean.
Hi, this is good stuff. You acknowledge that this is that these are estimates at the high level, and have you done anything to try adjusting those estimates a little bit to see whether you get more or less benefit if you say, give yourself a little bit more register pressure, a little less?
Loop invariant LICM heuristic works right from the beginning, just on all targets, and I haven't tried playing with it to achieve better performance because the numbers is pretty good.
Yeah, I just wonder if they could be better.
But then, sure, keep in mind that they could be live-through, right? And I don't account for them. They could be live-through values across the loop, and they just not accounted, yeah. And I mentioned that for GVN, I play a little bit with whether to compute the pressure per basic block that encauses the load or versus the loop. And turns out that the loop measure is more accurate. Mm-hmm. So surprisingly, not much tuning on these two heuristics. I assume that inliner, since it's module level scope, it would require more substantial effort.
Okay, thanks.
So in your approach, you look at each instruction individually to decide whether it's increase or decrease the register pressure.
Yeah.
Have you thought about the problem? Sometimes you have a cluster of instructions. If you're lucky, you move the whole cluster out, and then actually the register pressure goes down. Have you thought about how to solve that problem?
Yeah, actually, the heuristic allows that because once let's say we're in the threshold, and if the current instruction actually reduces the register pressure, we will promote it, and that will reduce the current life in, so that eventually this will allow new instructions to be hoisted.
No, the case.
So yeah, I noticed there's in some situations their whole chain of computation was hoisted outside the loop.
No, I'm talking
Is that your question?
No, the situation I'm talking about is if you look at individual instruction, it looks like it will increase the register usage. But it happens if you move several strongly related instructions, you move them all out, and then the instruction register pressure actually go down.
So I see your question. I'm answering that we are achieving this through incremental hoisting, basically considering each instruction one by one. So I'm said definitely should be case where you might miss something, but we are individually considering each instruction whether to hoist or not. Basically, we're not doing any backtracking, if that's the answer you want to hear.
Yeah, so the question is about what happens when the individual code motion seems doesn't work, but if you move a whole expression out or something like that, then it actually works.
perhaps we have such cases. Yeah, this is good optimization to try. Yeah, try maybe second one or third one. Yeah, in fact, yeah, but you're insisting of all three of them to be moved, 1, 2, 3, 4.
Right.
Then I'll say that then the second invocation of LICM, right, might hoist the remaining instructions. But yeah, I mean, the short answer, yes, we don't do hoisting in cluster. You just do one by one.
So the loop vectorizer has a register pressure heuristic. And can you make some comment about how its register pressure heuristic differs from the heuristic that you're using here?
Unfortunately, I'm not familiar with register pressure heuristic for loop vectorizer. So is it in terms of the vector register pressure or?
Yes. Well,
I mean,
yeah. I mean, it calls that TTI callback right, to get the number of registers, and it uses the scalar one when it's looking at whether it wants to interleave the scalar loop, and it uses the vector one when it's looking at whether it wants to vectorize. But I don't remember the algorithm offhand, and I was wondering how that differed from if you knew.
No, I haven't looked at this. Yeah.
Fair enough.
Is it loop vectorizer, right?
The loop vectorizer.
Okay,
yeah.
I'll take a look. Yeah.
Cool.
Thank you.
Yes. That's why it uses it, but yeah.
Yeah, it's probably similar. It does a backward traversal to find liveness and probably ignores live throughs.
So
yeah.
does it have?
It ignores live throughs.
Does it have good effect on performance? I mean, in terms of the.
I think so.
Okay.
It was important to add. So.
Yeah.
Sure.
Okay, so I have a few more comments just for you or just general people working on this. So I guess for loop invariant code motion, it's kind of interesting that hoisting the loads outside the loop is a bad thing because we generally think that reloading them shouldn't be too expensive versus leaving them there originally. And if there's an opportunity for hoisting them, would you consider maybe using a prefetch instead or?
Yeah, I think prefetching is. But the prefetching is usually for reducing cache.
Yeah, they're probably
memory latency. Yeah.
Yeah. For GVN, you mentioned not having loop info, and I don't know that there's any fundamental reason you couldn't like have an option where you would have loop info.
Yeah. Actually, to implement this, I added loop info and take advantage of the loop structure.
Okay.
I just wanted to be as simple as possible, but obviously it's not the case. Yeah.
Okay, and then I have to wonder how much of this. It's certainly good to place like an upper bound on how bad you want register pressure to become, but to some extent you may be working around deficiencies in the back end. So it'd be really great, for example, for the back end to have a global code motion pass where we do have precise register pressure tracking, and we just don't have that. And I wish someone would add it. So that you could use that to with high latency or reduce register pressure.
But my understanding is that the LICM and GVN in machine level are less aggressive compared to the ones version in optimizer.
Yeah, they are.
So I mean, then to ask you, what is the complexity of adding this, of using the register pressure tracking mechanism that is used in scheduler in those machine level passes? Is this a good option? I mean,
well, it is potentially expensive to do that. And I think we just wanted a cheap here. Well, those passes were developed before we had that. Yeah, that's probably the biggest answer. But I would really like to see those passes go away and have a more general global code motion.
At machine level?
At machine level, yeah. Where we have machine trace metrics to give us latency and critical path and precise register pressure.
So you still, just to confirm, you still see value of control register pressure at that time, right? I mean,
right. I'm saying we can do a better job controlling it at that time, and we may also be able to recover from poor register pressure at that time.
I mean, the closer you are to the actual hardware decision, the better decision you can make. Yeah.
So my most important comment probably is, I wish someone would do a better job at fixing rematerialization in the register allocator, and that I wonder how far that would go to resolving some of these problems. And I guess maybe the question for you then is, what kind of patterns did you see, and are they things that could have been rematerialized? And
well, the example, usually, I mean, for the particular benchmark, those examples, right? You have many globals, and I guess one big issue is scale replacement of aggregates, right? So you split all the global structure into individual elements, and then each one you're loading from. So this increases the pressure. But again, on the other hand, scale replacement of targets is a very important part, so it's good to split those, make them scalar, so they're available for scale optimization, right? In general, I mean. So it's a trade-off, I guess.
Thanks. Could you go back to, I think, page 16, the one you have a performance number, the speed up, right here. So in the case of MESA, so with the LICM ratio pressure heuristic, you got 9.1% improvement, and then the GVN one, you get 3.8. But then overall, you turn on both, it only has a 5.7 left. So that seems the one, the GVN ratio pressure heuristic, together working with LICM, it does very poorly. I could have just LICM ratio pressure and get that 9.1. And now I turn on the other. I only got.
I understand. I agree. Yeah, it's.
Do you know what happens there?
I haven't spent time, but yeah, the results are repeatable. I mean, you're running 3 times and picking the middle number. Yeah.
So I'm also wondering, just in general, right? Of course, ratio pressure is a bad thing, but I don't think we want to be too paranoid about it, right? In the sense that, for example, speed is bad, but you typically still hit the caches, right? So okay, so 3 cycles, and then plus do the sphere, do the field, and ratio pressure. Or so I mean, there's a trade-off between ratio pressure and say like the amount of computation you save, right? So again, I don't think we want to be too paranoid. It means that once you cross the threshold, okay, everything stops. That probably is overkill.
True. I mean, but my comment is we don't take into account the life-through life ranges. So it's not upper bound, I mean, we don't take into account life-through values. So we're not conservative, or rather optimistic, right? So I'm saying it's not, we don't count many possible life ranges that are potentially will cause spills, right? And then the heuristic allows. Yeah.
I think having the ability to track ratio pressure definitely is a good thing. And what you do with that, numbers, I think you want to be a little careful, right? You don't see, again, you don't say, you cross the number of registers, it immediately stops, right? Because there may still be things that, you let the register pressure go beyond your limit, right? And then but the optimization could still happen. And in some cases, that may still be a good thing.
Sure, yeah. So again, just to, we don't have hard stop. You allow the computation to continue, and if the next or third instruction does reduce the register pressure, we would hoist it. And then this open opportunity for additional hoisting. But I mean, yeah, I guess I can use some more complex data flow analysis just to be sure. But again, is it worth it? I mean, because the more complex you are to the heuristic, the more comparable it becomes to the actual optimization.
I guess it's quite good to know what happened at the MESA.
So,
sure.
So one possible explanation could be if both optimizations are sort of in the same place, then one may be taking the budget of registers for the other. So the first one that operates, if you're letting it use up the register budget that you have, it might consume and saturate your budget, and then the subsequent optimization might not have enough to go with.
And keep in mind that both LICM and GVN are called at least 3-4 times through with LTO on the pipeline. So some interaction might happen. Yeah. But given the big numbers, I mean, good numbers, yeah, I didn't have time to spend.
Okay, thank you again.
Thank you.